I'm so happy to have Mark Travis with us to kick things off for 2024. So Mark is the president of Arkenstone Exploration, with nearly 2 decades of mineral industry experience working with precious metals, base metals, and energy metals throughout the Western US. He has worked with major to junior mining companies from production to development, open pit and underground. And with his extensive background in uranium, it's going to be awesome hearing from him today about styles of uranium mineralization, the current market, and exploration.
Yeah, we're just going to go over the styles of uranium mineralization, a little bit about the current market, how you explore for it, and definitely leaning heavily on stuff that I've done. I'll definitely go over some of the styles of mineralization that I haven't worked with, but I won't go into depth on those much. I did present this at AEMA in Reno, updated a couple of slides, but haven't really updated it much since then. There have been some changes in the market, and so I'll definitely mention those. Just a little pitch for me. You've kind of covered it, Jessica, where I've been, what I've done, just in case you want to look me up. Thanks for having me. And let's start with what is uranium, right? And you've seen a little speck of it. For me, the UO2 uraninite pitch blend is kind of the immovable object as far as mineralogy is concerned. That gets hashed in with some vanadium and some potassium and different elements too to make some fun, pretty rocks. But mostly when you find uranium, it's just going to be kind of that gunmetal black, especially if you're finding it in a roll front. It is the heaviest of the primordial elements. There are things called transuranics, but those are usually made by, human causes. And it was discovered back in the 1700s, but obviously its radioactivity and its use as a nuclear power energy source was much later. And its most abundant isotope, it is element number 92, but its most abundant isotope is 238. But 235 is your fissile element, and that's what needs to be enriched for power generation. And yeah, well, that's probably enough for that slide. So with this is one of the things I did update was the actual Kitco blurb there. It peaked recently at 106 per pound, came back down to 100 here, but I think a triple digit uranium is not a unforeseen. This is definitely kind of, I think, the new norm going forward. But for context, we can look at the last cycle. 2007 was when we did hit 136 uranium. So I'm not sure what that's going to be adjusted for inflation going forward. I'm assuming we'll probably get up in that ballpark again. And you can kind of see where it's been. That large kind of lull from 88 up until 2007 was kind of a 20-year bear market there for uranium. And but I think the reality of its need for use in nuclear power is going to continue to drive the market upwards. So that's one half of the market, right? Just the price, what it's doing. But I think the other half of the market is actually why the price is doing that. And I think a lot of it has to do with, you've probably attended webinars and lectures about the push for electrification. We're going to be building all these electric cars, but not too many people have been asking, where does that outlet lead? If I'm taking an electric car home and plugging it into a coal-fired power plant, it's still a carbon-based car, at least on the macroscopic level. And so another thing that's changed recently is the NRC has actually approved, it's the Nuclear Regulatory Commission, they've actually approved these small modular reactors, SMRs, and that is the first new approved reactor design in the last 40, 50 years. It takes them a while to approve something, I would think, or maybe that just wasn't the right design, who knows. But these are great little units. They're meltdown proof, and they can be built indoors at a factory line, which is one of their advantages as well. drives some costs down. Other things that are happening is we've got some private industry moving in. They're replacing coal-fired units and coal-fired power plants. One in particular, Kemmerer, Wyoming, the Terra Power Group is already moving on that. And I view uranium is just as critical as lithium or the other battery metals. And what I didn't update on here was since I put this together, I think it was just last week, Japan has actually listed uranium as a critical metal. So that's a good thing. And uranium has been a critical metal as far as the USGS list in the past. It's just not currently on that. So further into the market and kind of maybe getting on my soapbox here, I view uranium as kind of humanity's new fire. We've been using carbon-based fuels since we were cavemen. And I think we finally have gotten to the point where we've got a material that can, give us that energy that's more than just, burning our different carbon sources of fire. And 1,000,000 to 1 is kind of the rough ballpark figure here of the energy density per unit of material. Just to quote one particular comparison, 1 kilogram of uranium is 24 million kilowatt hours compared to 1 kilogram of coal. It's just 8. So that's actually more like 3,000,000 to 1, but who's counting, right? The point here is that I think nuclear power, if we learn how to harness it correctly and deal with the waste properly, it can be a lot greener and cleaner than any of our other sources. So I think that's the tail end of the market story. And then sort of a little bit of history and some fun 1950s kind of some stuff here. But so post World War II, the Atomic Energy Commission is formed. This is to regulate the nuclear power. I don't know why they were thinking that they were going to have to regulate both military and civilian applications of nuclear power, but more importantly, by 48, the AEC became the only legal purchaser of uranium, and they decided that they would purchase from private mines, and this opened the doors for kind of the uranium boom, especially out here in the West. And it kind of dovetailed in with the post-World War II atomic age of the 50s. Later, the AEC has now become the Nuclear Regulatory Commission, and they don't do what they used to do, which was hand out Geiger counters and pay people to go stake claims and go find that uranium. But what's interesting is this uranium rush, the game that you see here, is it was actually a real. I knew a guy who actually had an original copy of the Uranium Rush tabletop game. But back then, even Popular Electronics had a uranium prospecting issue, and there's newspaper articles about someone hitting it hot. And that little prospectometer right there is very similar to the unit that I was using at the beginning here, just a typical scintillometer. And a little more on the history. Most of the major U.S. reserves are kind of, you can see on the map there, focused here in the kind of the granitic core and the oldest parts and pieces of the Western Cordillera. And people like Madame Curie and Henri Becquerel, pictured here as well, they obtained their radium samples from pitchblende ores in the Paradox Basin. It was actually vanadium mines back then. They weren't known as uranium mines at the time. And most of the legacy mining is kind of centered around the Four Corners area, and more of the younger discoveries are out from there. There's a lot of producing mines down in South Texas, up in Wyoming these days, and the Panhandle of Nebraska's got some good deposits as well. Before we get into kind of the styles of mineralization here, I just kind of put together this Venn diagram first to help myself understand some of these kind of how things work in these systems. But general controls, you've got to have the right kind of lithology. Porosity and permeability are key. And then another one that's a reoccurring theme is a reductant, some way of kind of reducing the fluid. And a lot of that is uranium is very similar to like lithium, where it gets very soluble really quickly with any amount of water and oxygen in that water. And so that's why these ancient aquifer waters and a redox boundary and kind of these trapping areas in the sands can be very lucrative for when you're actually looking for these uranium deposits. So just kind of an overview, and I don't know, Venn diagrams are fun. So just to get into the styles of mineralization, I think when I was reviewing all the different styles of mineralization that were out there, many of which I've never worked with, I think there was a dozen or more individual classifications, but I'll just go over a couple here. Unconformity are definitely your Athabasca Basin style, really much older rocks in shear zones and the like. Sandstone hosted, I kind of break it out into both the tabular or Mesozoic hosted varieties, and I've worked more directly with the tertiary younger roll fronts. And I see those more as a primary dissolution redox boundary, whereas the Mesozoic tabular um, varieties, I think, have been remobilized is another term for them. And then, of course, you get these humate carbon-bound ones where famously down in the Uravan district, you would find entire old logs, fossilized logs that have been completely, uh, you know, mineralized with uranium. And one of the more interesting ones too that I've done some research on, never worked with directly because aren't too many of these mines still open, is the breccia pipe style. I'll go over that. You also find volcanogenic. Nevada's McDermott caldera north of Winnemucca is a classic example of these kind of stratiform volcanogenic ones that form underneath rhyolite caps. Um, and then one that I listed here, but I've never worked with, it'd be interesting to know more about, are these paleoplacers that are found in conglomerates. I guess maybe that'd be similar to the Witwatersrand strand down in South Africa. But, most of your significant grade and mineable quantities are going to tend to fall into either the unconformity or the sandstone hosted varieties. And I'm going to focus on the sandstone hosted varieties. That's what I've got most of my experience in. And yeah, it's just easier to talk about. But first off, in the different styles of mineralization, I just thought, if no one's ever seen one of these breccia pipe deposits, it's worth looking at and kind of seeing how these are put together. Um, Probably the highest grade sandstone hosted variety that you'll find down in the Western US. A lot of them are kind of locked up in some no-go zones these days, north rim of Grand Canyon and whatnot. It's funny how they found these originally was that circular depression on the surface was what gave them away, and how they were able to actually see these collapsed breccias. And it was actually the Coconino sandstone that collapsed down into the Hermit Shale throughout most of these breccia pipe areas of the Arizona Strip and Grand Canyon. And it was the Coconino sandstone that created the porosity, and then the Hermit Shale was then created that reductant, and then your mineralization most likely came from the fluids that were moving up through the dissolution of the breccia. And these have been mined successfully back in the day via underground shafts and stopes. You can't really see it on these pictures here, but there's some diagrams of how exactly they shafted down and kind of declined into these bodies. To drive this point home, courtesy of Gene Spearing, who's done a lot of work on this, he gave me this last one here, this really nice detailed diagram here, but I also took a picture of the Energy Fuels one when I was down there in Kanab looking at some of that stuff. But this is really quite interesting to show that these could be quite a prolific deposit type out there where you may or may not see all of the surface expressions of these breccia pipes. And I thought this was a really cool block diagram just to kind of show exactly how these can exist, but then also to show that we probably found all the easy ones, and if there are ones that are more blind targets, we have to work a little harder. So the breccia pipe stuff is fun. but I haven't worked with those directly. The roll front style is definitely something that I've worked with directly, and I'll go over kind of the anatomy of one here. But yeah, I'll mention here that they were called geochemical fronts, and I think early on they were called that to distinguish them from the tabular fronts in the Mesozoics and the Colorado Plateau. Um, but there's a lot of debate on whether or not they're practically the same thing. I kind of classify them as younger versus older is how I differentiate between the two. Um, how I work with them and where I've seen them have a lot of production and mineable quantities. They're hosted in these tertiary continental sourced fluvial sands, and that redox boundary is where you've got the, the oxygen-rich waters coming from surface down at depth. At least that's one end member of how these are formed. And the anatomy here is that you have tails back behind your main ore body and a nose out front. And tails and nose are kind of the terms that are thrown around, but those are important when you're exploring for these things because you need to know if you're behind the system or in front of the system, right? And then there's some other hallmarks about, is your interior sandstone oxidized or is it still reduced out in front? Those sort of things are important to look out for when you're actually drilling for these things. And so here's some pictures I took recently of my trips out in Wyoming, and I just thought I'd mention kind of some of the internal packaging of these fluvial systems can create their own reductance, and the fact that you might have these little mud drapes and stuff coming through, and how these fluvial systems kind of stack can be complex. Let's just put it that way, right? And then the way that the different uranium can mineralize and form concretions and different discolorations is something you have to look out for as well. And then just to kind of riff on this Venn diagram again, where's the sandstone, where's the porosity, where's the reductant, just to kind of get you thinking about those. So, and then to kind of go back to the other sandstone hosted varieties that I've mentioned, these tabular rolls, most likely redistributed mineralization would be my argument. The Morrison Formation of the Uranium mineral belt is very famous for these. There are some smaller deposits found in the brushy basin member, but most of your mined material is in the salt wash. But then also there's other places down that Cedar Ridge photo is taken along the Arizona Strip. There's Chinle Formation deposits, and actually pretty much throughout the entire Mesozoic section, you can probably find some formation in the Four Corners, Western US, where there might be some sort of mineralization, especially if it's a sandstone within the Mesozoic units. Some more famous than others. Might as well go over some of the mineralogy. I think my key takeaway here is that the UO2 doesn't go anywhere. The uraninite or the pitch blend just gets remobilized into other things like carnotite and autunite and coffinite and all those different, pretty minerals. Mostly what you're going to find out in the field is just uraninite pitch blend materials, unless you're working in Uravan, and then you'll see all of these pretty colors down there. Another takeaway from here is that crustal rocks, just under 2 ppm by weight, but the seawater is upwards of 3 ppm. So if we ever get really good at fishing for uranium, we might be able to grab it right out of the seawater. That's halfway a joke because actually the Japanese have worked on that using fish nets made out of shrimp shells. Actually, they tried to use resin beads, but it's cheaper to use shrimp shells. Still not cost effective, but might be someday. And then just to kind of correlate the different kind of deposit types with maybe what the mineralization might look like. For pretty much anything that's got the fun, complex colors are going to be more secondary minerals, remobilized materials. This is actually a piece of pitch blend, the circular number D down here that came from a breccia pipe. and that's straight uraninite just in the black blobs there. And you can see some blebs of pyrite, and then that's just the mashed up breccia material, breccia, matrix supported breccia at that point. So maybe we'll go through some deposit examples here now that I've kind of rolled out some of the different deposit types. Here in Nevada, the McDermott caldera, it's stratiform volcanogenic deposits, typically underneath a rhyolite cap, definitely hosted in tuffs, might have some associated fluorine, those sort of things. Definitely granodiorites and rhyolites, and so on the felsic end of things. But it's interesting to think that this is associated in near the Yellowstone hotspot track, and that maybe a deep sourced lava, or at least the heat engine from a deep source lava, could have something to do with the uranium dropping out in these calderas. Another deposit examples, actually the Gas Hills, Wyoming. I've done work out there 10 plus years ago, and this A to A cross section is just kind of going roughly north to south here, from the Granite Mountains to the Owl Creek Mountains in central Wyoming, and it's just a really long syncline, and these smaller things that are the smaller veneer, that's the Wind River Formation over on the south side of the cross section is where the uranium is hosted here. And but so this was just to kind of show kind of the regional scale of where this sits. And then to show an exposed roll front, this was actually a picture taken during some reclamation activities out in the Gas Hills, Wyoming. And it shows the oxidized sands on one side, the reduced sands on the other side, and probably most of that black material is actual mineralization there. And then here's a roll front exposed in the open pit bottom itself. They would mine a lot of this stuff by scraper trucks, just belly scraper trucks that would go through. They didn't really have to blast too much of this material, and grade control was just done with a scintillometer, and they would go out there and mine it that way. And through the 50s to the 80s, there was over 100 million pounds of U3O8, and there were several mills that were in operation out there at the time. But a lot of this was walked away from in the late 80s when price dropped out, and a lot of this stuff was just put to bed, with resource still sitting in the ground. So we've gone over some of the mineralization, we've gone over some deposit examples. Now, how do we explore for these things? And I think what I'd like to introduce is, when you're exploring for roll fronts, or just uranium in general, but especially roll fronts that are individual stacked sands, you can get complexity in multiple dimensions. You can get it with its sinuosity in plan view. They can really start looking like a bowl of spaghetti. And then individually, at depth, you've got this on echelon stacking, and that's what you want. You want a lot of stacking on top of sinuosity, and that's because that's how you'll build a lot of resource in one area. Traditionally, this is, and still to this day, it's drilled by mud rotary methods, the same sort of drill rig that a rancher would put a well on their property with. But then we throw some fancy tools down the hole. I don't know if you can see in that bottom picture, there's that little white truck there. It's got a boom on it. That's actually our geophysical truck. That has a tool that reads gamma, SP resistivity. I think it also does temperature and obviously stuff like deviation and whatnot too. That'll give us just kind of an indirect assay for uranium. The prompt fission neutron tool, which there are only a couple of these days anymore, that's the only direct assay method of uranium that I know of. But yeah, usually these are quick, shallow drilling programs. I mean, the program I headed up this last year, we were doing 3 to 5 holes a day, 1,500 feet of drilling. And so it was really nice. I mean, and with this sort of exploration, you get results instantly, and so you can kind of pivot and shoot from the hip sometimes with where you need to put your next hole, which is nice. So what does current mining look like for these? I mean, I showed you some pictures of open pits and discussed underground mining and all that sort of stuff. But typically, the way that these are mined, especially in the Powder River Basin of Wyoming, and in South Texas, and in Kazakhstan, and any place where this is amenable to do it this way, is the ISL or ISR leach or recovery method. And it's what that picture looks like up there in the top. It's just a well field. We You don't have to move any of the dirt. You just have to drill some wells, but you have to drill them in a very exact way so that you can actually inject and collect fluids in a way that will actually, affect the ore body. Because at the end of the day, you've cut out the entire mining process here. You've gone from a drill hole to a process facility, and it's a pregnant solution that's being loaded onto resin beads at the end of this process. So it's kind of a cool method. It's mostly how it's being mined these days, and especially if it's these roll front style deposits in a sandstone, you almost reverse the flow. I'm actually showing this diagram somewhat incorrectly, but it's fine. The idea is that you push the uranium the opposite way it came into that roll front. And really, I know there are places that use sulfuric acid, but here in the U.S., we just use some oxygen, some hydrogen peroxide, sodium carbonate, CO2, stuff like that. And from everything that I've been looking at, that's your end product is the yellow cake. It seems to be the most cost-effective method these days for getting this sort of stuff done. And I think a lot of that has to do with it's more environmentally friendly, at least at surface. So taking that idea, I know the Gunnison project, Excelsior Mining Corporation down in South Arizona has been trying to use the in-situ method to mine for copper. And it makes you wonder, are there other maybe low-grade, troublesome to permit deposits that could be leached? Obviously I've been talking about uranium this whole time, and maybe this slides out in the left field for some of you guys, but I just thought it'd be a way to think about modern mining. Maybe you don't have to dig it up to mine it. This is a fun little infographic showing uranium production. There's really only been 70 years of it, 70 plus years of it now. And back in the day, USSR and the US were big powerhouses for that, obviously for the Cold War and stuff like that. But I think since then, things have changed. Kazakhstan's a big producer these days, and some of the other players are still there, but it just seems to be like the field's maybe widening and there's other players coming through. And then just to show again kind of where the different uranium resources here are in the United States, at least. And oh yeah, and a safety share. Why not have a safety share at the end? What is normal here in the US? Norm standing for naturally occurring radioactive material. I guess there could be a misnomer out there about the fact that radiation is somehow foreign to us, but it's not. We're standing on it every day. That pie chart kind of shows just how much sort of natural occurring radioactive materials you're exposed to on a yearly basis and kind of where it comes from. So, and then I'll end with question slide.
Thank you so much. That was really interesting. So thank you.